Module 8, Example 2. Again, we're going to explore the effect of sample size on the distribution of sample statistics. It reads as follows. Suppose we're interested in understanding the population parameter mu. We hypothesize that the true value of the population parameter is 250. So our null hypothesis is mu equals 250. And suppose the population standard deviation is given to us to be 10. So I go out and I collect a sample of size 80. I get a sample mean of 252. My friend Bob also goes out and collects a sample, but he gets a sample size of 40, but he also gets a sample mean of 252. So notice, Bob and I have the same sample mean, 252, but I had a bigger sample size than Bob. All right, so let's explore this. In the last example, we discussed this idea that the effect of the sample size is that bigger sample size will produce a distribution of sample statistics that's narrower, and a smaller sample size will have a distribution of sample statistics that's wider. So it must be the case that the distribution shown here in the bottom is the distribution of sample statistics from the bigger sample. And the distribution at the top must be the distribution of sample statistics from the smaller sample size. So why is it that it does this to the distribution of sample statistics? Well, the answer lies in that formula for standard error. Remember, standard error is the standard deviation of this distribution of sample statistics. And when we have quantitative data like this, it is given by the formula sigma over square root of n. We were told in this problem that sigma is equal to 10. So the standard error of the distribution at the top is 10 divided by square root of 40. And the standard error for the distribution at the bottom is 10 divided by square root of 80. Now notice the difference. The distribution at the bottom has a bigger sample size. So in the denominator of the formula, you're going to be dividing by a bigger number. And overall then, it's going to come out smaller. If I pull out my calculator, I would find that the standard error of the distribution at the top is 1.6. The standard error of the distribution at the bottom is 1.1. So if I now go ahead and label each distribution, the null hypothesis was that mu equals 250. So that means each of these distributions has a center value of 250. But at the top, the distance between each vertical line is 1.6. And the distance between each vertical line and the bottom is 1.1, which is going to make it narrower. If I go through now and I label each, starting at 250 in the top, I add 1.6 over and over to label each vertical line. And I'll do the same for the distribution at the bottom. Each vertical line is corresponding to a standardized statistic distance. So standardized statistic on this distribution would be the t-score. I'm going to label those in blue. So the t-score of 250 would be 0, because it's 0 standard deviations away from the mean. And this first vertical line to the right is a t-score of 1. The second vertical line to the right is a t-score of 2. Going backwards, it would be a t-score of -1 and a t-score of -2. Similarly, in the bottom distribution, the middle has a t-score of 0, 1 up is a t-score of 1, 2 is 2, 1 below is -1, and 2 below is a t-score of -2. Okay, so we can see then that in our distribution of sample statistics, the bottom one is narrower. It's saying the distribution of expected, usual, normal sample statistics really is ranging from 247.8 up to 252.2. So if you have a sample size of 80, it would be normal, usual, and expected to get a sample mean somewhere between 247.8 and 252.2. Remember, if you go beyond 2 standard deviations, beyond a t-score of 2, then you're getting in that realm of unusual, unexpected. So in the bottom distribution, if you did a sample of size 80, it would be unusual for you to get a sample mean bigger than 252.2 or smaller than 247.8. But that's different than what happened up here in the top distribution when we had a sample size of 40. When you have a sample size of 40, it would be normal, usual, and expected to get a sample mean somewhere between 246.8 and 253.2. because those are within 2 standard deviations. It would be unusual to see a sample mean above 253.2 or below 246.8. Now notice the difference then. That's a bigger range of expectations than we saw below in the distribution at the bottom. All right, finally then, it did say that we actually saw a sample mean of 252. Bob and I both got a sample mean of 252. So in the top distribution, when the sample size was 40, you'll see that 252 is about here. And so it has a t-score of 252 minus 250 divided by the standard error, which is 1.6. If you calculate that out, you will see that the t-score is 1.25, meaning this sample statistic of 252 is only 1.25 standard deviations above the mean. It's not unusual. The null hypothesis is plausible. It's plausible that the true value of mu is 250. In the bottom distribution, 252 is very, very close to this edge of normal, usual, and expected. It's almost touching that t-score of equaling 2. When we find the t-score for this value, it's going to be extremely close to 2. When you do the calculation this time, you see that the t-score is 1.8, very close to 2. However, it is still in the realm of normal, usual, and expected sorts of statistics to get. It's not equal to 2 or more than 2 yet, so I still would say that the null hypothesis is plausible. I still would conclude that it's plausible that the true value of mu is 250. However, note, when we made the sample size bigger, it made the distribution of sample statistics narrower, which made our observed statistic more unusual. It would have a smaller p-value than the one that we saw in the top distribution. It does have a bigger standardized statistic than one we saw in the top distribution.